is going to. Today we have Dr. Tong Huang, postdoctoral researcher from Texas A&M. He got his PhD there under Professor Lu Shi. And so we've had a working relationship with them, and we have joint projects. And he's going to talk about anomaly management in massively digitized power systems. And just a few logistic questions. Please send your questions, clarification questions, any questions that you may have in chat, and I will look and maybe interrupt you, Tong, so that we make it a little bit more interactive. On Monday, we had somebody from National Grid. It was very interactive. It's good to make these things interactive also, but depending on how much material you have to cover, we make it less or more interactive. So what do you prefer, Tong? Do you prefer to just have clarification questions and other questions at the end, or which way would you like?
I prefer to start all questions at the end. This presentation okay. will take 45 to 50 minutes.
Okay, perfect.
Yeah.
Okay, perfect. So welcome, and please, we are looking forward to your talk.
Okay. Thanks, Maria, for the introduction. I would like to thank Maria and Dan for inviting me, and thank everyone for being here. Today, I would like to talk about anomaly management in massively digitized power system. So the power system is in the trend of digitization, where you see more and more digital solutions are being integrated to the power grid. So as an example, we have more advanced sensor than before. This is a PMU synchro phasor coverage 10 years ago. At that time, we only have 200 PMUs, but this number grows to 10 times larger than before. This is today's PMU coverage in North America. So the second example is about power electronics interfaces. So many countries aim to shrink their carbon footprint by integrating more and more renewables to their energy systems. As these renewable resources interface with the grid, with the AC grid through power electronic devices. So as a result, the system dynamics is not only defined by the giant rotating machines, but also by the algorithms embedded into this power electronics interface. Furthermore, mechanical protection solutions are being replaced by their digital version, and at the grid edge, we have both communication and computation capacity. So the grid digitization brings both challenges and brings both opportunities and challenges. For opportunity, sensor proliferation enhances the grid transparency. So we can leverage the streaming data to detect, classify, and locate anomalies in real time. Here are some related work using synchro phasor data to enhance situational awareness of a system operator. For example, we can use streaming data, monitor oscillations. We can achieve early event detection by using streaming data. On the other hand, the grid digitization also causes challenges. The first challenge is about the cyber threat. Many decision-making in the digitized grid possess such a feedback structure. Essentially, we have a controller which makes decisions based on the distributed measurement from the grid. So in such a decision-making structure, here comes the cyber vulnerability where attacker may compromise the grid by maliciously intruding into the measurement. If that happens, all decisions made by the controller may be wrong, and the whole grid may be compromised. This concern has been noticed by the new administration team. So another challenge is about physical security of the grid with the inverter interfaces. So such a challenge exists in both transmission system and distribution system. For example, in transmission system, we want to build more and more solar or wind farms. This renewable energy interface with the AC grid through power electronics, through inverters. So the inverter malfunction may cause the renewable curtailment. Here is a real-world example. In 2016, so the inverter malfunction caused around 700 megawatt PV generation to trip. So similarly, in the distribution system, we may have more and more solar panels, and this solar panel interface with the AC distribution system through power electronics. It is very challenging to manage a distribution system with so many power electronics and non-dispatchable resources. So in this presentation, we will show two concrete examples to show you how to leverage the emerging opportunity and pressing challenges in a massively digitized grid. The first part of this presentation will talk about false oscillation localization. The second part of the presentation will talk about the challenge, and we propose a learning-based transient stability assessment framework for networked microgrid. So let's first talk about the first example. This example is about a synchrophasor data-driven method for false oscillation localization and resonance condition. And here are these are two key references for this work. And this is a joint work with Professor Ferris, Professor Kumar, and Professor Xie. Professor Xie is my PhD advisor. So first, let's remind you what is a false oscillation localization problem. Consider power system as a black box with some input and some output. Suppose one of the input varies periodically, you will observe oscillations as an input as an output. This oscillation is called false oscillation. Accordingly, this periodic input is called the source of the false oscillation. Different measurements have a different geographic location from the source. Some are close to the source, some are not. So the question is, without the knowledge of the input and the system model, how do we pinpoint which measurement is near the source only by the output measurement? This problem is called a false oscillation localization problem. You may think this problem is simple, right? Because you may think the measurement near the source will exhibit the largest oscillations. However, that's not always true. Challenge comes when the injection frequency is near one of the natural frequency of the system. That is, the resonance phenomena is triggered. The bottom figure shows a counterintuitive example, shows such a resonance oscillation under the resonance case. In this diagram, the red measurement is a measurement near the source, but it does not exhibit the largest oscillatory magnitude. So false oscillation under resonance condition is more than a theoretical concern. Here is a real-world example. So in this example, one power plant at Alberta has a 20 megawatt oscillation, and such an oscillation causes a 10 times larger oscillation at the California-Oregon intertie. The distance between these two places is over 1,000 miles. The question is how we need to develop an approach that can locate oscillation source even when resonance happens. How to solve this problem? We formulate this problem into a matrix decomposition problem. So we can, after collecting all synchrophasor data, we can organize them into a matrix form. Each row of the matrix represents the time series recorded by one PMU, and each column represents the snapshot of all PMU measurement at a time instant. Then once we get all data, we can organize them into a matrix form, Y, and then we can decompose this Y matrix measurement matrix into a low rank matrix and a sparse matrix. By tracking the largest element in the sparse matrix, hopefully we can track the source. So the next question is how to decompose a measurement matrix Y into a low rank matrix Z and a sparse matrix X. So here is how we solve the problem. These three formula just translate this English sentence into mathematical formula. Essentially, we want to decompose the matrix Y into a low rank matrix Z and a sparse matrix X. The rank of the matrix is upper bounded by R, and the number of this is L0 norm. The non-zero element, the number of non-zero elements in the sparse matrix is upper bounded by P. Unfortunately, this is a non-convex optimization problem because due to this rank and L0 operation. For engineers, these upper bounds R and P are unknown. So we need to reformulate the problem. So here is the reformulation. So in the new formulation, we're trying to find a matrix X such that the sum of these two terms is minimized. The first term is about nuclear norm. Basically, is the sum of the singular value of the matrix, and the second term is the L1 norm, is the absolute sum of all elements in the X matrix. So this is a convex optimization problem. The good thing, another good thing about this formulation is that there is no need to know upper bound R and P, and we have an efficient algorithm to solve it. And lambda is a user-defined parameter, and this reference tells us we can let lambda equal to this number. So next, we test this algorithm in a IEEE benchmark system. And this is the IEEE 68 bus system. So in this system, we create 44 counterintuitive cases. So what do I mean counterintuitive? So here is an example of a counterintuitive case. In this case, the true oscillation source located at within this red solid circle, but the most severe oscillation appear in the blue circle. So system operator may think the generator near the bus 40 is the one causing the false oscillation, and they trip the generator 14. But if they trip this generator, and the oscillation still exists because the true source located at generator 13. We need to correctly locate the true source. So it turns out that this algorithm is pretty effective. So we can achieve over 97% accuracy even under resonance cases. So we, as I mentioned, we have 44 counterintuitive cases. We get correct answer for 43 of them. There are one wrong case. So let us examine the wrong case. So in the wrong case, the true source located in the dashed circle, but the source we identified located in the solid circle. So even though they are not identical, they are pretty close to each other. So in other words, the seemingly wrong result can effectively narrow the searching space. So we tested this algorithm using synthetic power grid data. Next question is how does this algorithm work in reality? So we are fortunate to have a collaborative project with ERCOT, and ERCOT provides us some false oscillation data and asks us to locate the source for them. Based on the algorithm, we develop a false oscillation tool for them. The tool essentially have two steps, two case stages. At the first stage, so the first stage aims to pre-process the data. Essentially, it can organize the PMU data into a matrix form. It selects the data of the interest and filter out the high frequency component. Once we get a clean data matrix, we can decompose the matrix into a low rank matrix and a sparse matrix by tracking the largest absolute element in the sparse matrix. We can pinpoint the source. So ERCOT provides us 3 false oscillation cases, and we conduct the test without knowing the true source. Once we get the result, we email them, and the ERCOT confirms the correctness of the result. So the last question is about, because the power system is a safety critical infrastructure, so the algorithm applied for its decision making needed to be justified by physical laws. So how to justify the performance of this data-driven algorithm? So in this approach, we just use the data from the power grid. We didn't use any physical model, such as the system parameter and system topology. How to justify the performance of the algorithm? Here is one possible interpretation for this algorithm. First, we do physical analysis. Based on the state classical control theory, we can write down the time domain solution to the measurement. So once you do that, this measurement can be decomposed into 2 components, resonance component and resonance-free component. So let's scrutinize these 2 components one by one. So for the resonance component, if you collect all resonance components for all measurements and organize them into a matrix form, so you can prove the resonance matrix has rank 2. So this is our first observation. For the resonance-free component, so here is the observation. So the bottom diagram visualizes all the measurements in a synthetic grid. So the red curve is the measurement near the source. It is a counterintuitive source because the measurement near the source does not exhibit the largest magnitude. However, if we exclude all resonance components for all measurements, you get a realization for the resonance-free component. And the resonance-free component essentially tells you where is the source, because the largest resonance-free component corresponds to the measurement near the source. So this is the second observation. Resonance component tells you where is the source. So now we are ready to make the connection. So for the resonance matrix, it has a rank 2. It is a low rank, so it should be captured by the low rank matrix. For the sparse matrix, it should capture part of the resonance-free component, and the resonance-free component essentially tells you where is the source. So let me have a very short summary for the first part. So we propose a data-driven way for false oscillation localization, and we use robust principal component analysis to conduct the matrix decomposition. We validate the performance of the algorithm based on both simulation data and the real-world data. And finally, we provide one possible interpretation for the method. So let's proceed to the second section, the second example in this presentation. We're trying to address the physical anomaly due to the power electronics interface. So the example we use is a learning-based transient stability assessment framework for network microgrid. So these are 3 key references for this work. So let me remind you what is a microgrid. So microgrid, so this diagram shows the physical infrastructure for a microgrid. So a microgrid is just a small-scale power system where we have a generation resources. The generation resources interface with other components through power electronics interface, and they are networked with each other through a microgrid network. Here, we assume there is a power electronics interface between the microgrid and the rest of the system. So a future distribution system can be considered as a networked microgrid. So we have this diagram shows a distribution system with n networked microgrid. So in such a physical architecture, there are some large disturbances. So the disturbance may come from both operational mode change and the disturbance at the network side. So for example, each microgrid have two operation modes, islanded mode and a grid connected mode. So when they change from one mode to another, this will cause large disturbances to the grid. And also disturbance may also come from the network side. For example, the line tripping can be considered as a large disturbance for the distribution system. So the transient stability assessment is critical for both planners and system operators. For system planners, it is important because they want to make sure when they connect every pieces together, the system won't blow up. And for system operator, it is a transient stability assessment provides some situational awareness by telling them if the system will bounce back to the normal state following a large disturbance. So in this example, we only talk about the stability of the networked microgrid with the power electronics interfaces. So next, before talking about stability, next let us describe what the interface dynamics of the microgrid. So in this example, we assume there is a power electronics interface between the microgrid and the distribution system. The good thing about this interface is that it can simplify the control task of the distribution system operator. Instead of control hundreds of DERs in the microgrid, so the system operator only needs to coordinate several interfaces. The second advance for this interface is it allows for power sharing between microgrid, meaning to determine how much power each microgrid should contribute when in order to eliminate the power unbalance. So the interface dynamics depends on the control strategy deployed in the power electronics interface. So typically we have a frequency, in the literature we have a frequency droop control and an angle droop control. Frequency droop control take action based on the frequency measurement, and angle droop control take action based on the angle measurement. And the droop control requires communication because angle requires a common reference. So in this, for simplicity, in this work, we assume each microgrid have a angle droop control. These two first-order differential equations describe the nodal dynamics of the microgrid. So the underlying assumption for this dynamics is that we ignore the fast dynamics in the inverter. And based on some simulation, we can show that these two first-order equations can reflect the general trend of the nodal dynamics. And also we have a network constraint, which are nonlinear power flow equations. So writing them in a compact way, we have x dot equal to f of x. Vector x is a state vector, and function f defines how this state evolves in terms of time. So the next question from the system operator is the system stable, and how large are the disturbances that the system can tolerate? This is the two questions we're trying to answer. Actually, these two questions can be answered by very classic control theory. The first question is about stability certification. So what do I mean by stability? So this defines what is stability in the Lyapunov sense for an equilibrium point. Essentially, it says we can stay arbitrarily close to an equilibrium point by start sufficiently close to the equilibrium point. How to certify the stability? 100 years ago, Lyapunov tells us if we can find a function called Lyapunov function, then we can certify asymptotic. We can certify the stability for an equilibrium point. So what is the Lyapunov function? Lyapunov function should satisfy two conditions. The function should be positive definite in a valid region, and the second condition is about the time derivative should be negative definite. The second question is about how to quantify the magnitude of the disturbance. We can leverage this concept called a security region, or region of attraction. So what here is the definition for the security region or region of attraction. So if this red region is a security region, it means if we start arbitrary point within this circle, the system trajectory will tend to the equilibrium point. And the system trajectory will never be outside this red region. This is the definition for the security region. So the question is not answered by Lyapunov is that, well, how to find a Lyapunov function? So we are a new generation of power engineers, and we have witnessed so many successful stories in other machine learning in other domains. So the question we want to ask is, can we learn it? Can we learn a Lyapunov function from state space? So answer is yes. So first we can assume the Lyapunov function have a neural network structure. So the bottom figure shows the neural network with just one layer. In this neural network is nothing but a function. We have input x, and we have a scalar output. The input can be interpreted as the state variables, and the output of the function can be interpreted as the Lyapunov function evaluated for the input state. So this neural network has some tunable parameters, weight factor and bias factor, W and B. So the question is how to tune the parameter such that the neural network behaves like a Lyapunov function. And in other words, what is the cost function to tune the neural network? So here is the cost function. This long equation essentially have two terms, the red term and the blue term. If you scrutinize this cost function, you will observe that if one condition of the Lyapunov function is violated, so the cost function will introduce a positive penalty. For example, if the first condition is violated, the first condition is the positive definite of the Lyapunov function. If it's violated, so the red term will introduce the positive penalty, and the blue term will introduce the penalty when the second condition is violated. The second condition concerns the time derivative of the Lyapunov function. So the next question is we need to minimize the empirical Lyapunov risk by selecting tunable parameter theta. So it can be solved by gradient descent algorithm or its variant, such as backpropagation or Adam algorithms. So is it enough? No, it's not enough, because so far we just checked the satisfiability of the two conditions for the state enumerated. We don't know the satisfiability of the condition at the other portion of the state space. And we need a rigorous way to check if the two conditions are met in the state space. If we can find if counterexamples are found, we add them to the training set. If no counterexamples, we claim the Lyapunov function is found. What do we mean? What do I mean by counterexample? The counterexample is nothing but the samples violated at least one condition of the Lyapunov function. Basically, in other words, the counterexample should satisfy these two logic formula. The first part of this formula just equivalent to the violation of the first condition, and the second part related to the violation of the second condition of the Lyapunov function. So we need to search examples that satisfy this logic formula. And in other words, how do we check the satisfiability? Fortunately, we have a tool called satisfiability modular theory. SMT solver can help us to find which sample satisfy this logic formula. And for the SMT tool, it has a very important property. It said if the SMT solver concludes the logic formula is unsatisfiable, then it is guaranteed to not have any solutions. In other words, if SMT2 claim there are no counterexamples, so it suggests the function we find is strictly a Lyapunov function. So that's the whole procedure for finding learn a Lyapunov function from the state space. So we first start from the linearized system, because if the linearized system is not stable, we don't need to check if there is a Lyapunov function, because the system won't be stable. This statement is called the Lyapunov linearization technique. If the linearized system is stable, then we trying to quantify the disturbance that the system can tolerate. First, we randomly enumerate some samples in the state space. We form it. We collect them as a training set. Based on the training set, we can learn the parameter based on the gradient descent algorithm. And then we search based on the SMT tool, we search for counterexample. If there is a counterexample, meaning the function we find is not a Lyapunov function, we add the counterexample to the training set and return the parameter for the Lyapunov function. And if we cannot find a counterexample by SMT solver, we claim we find a Lyapunov function. This figure visualizes the typical shape of the Lyapunov function. It is a positive definite, and its time derivative is a negative definite. Once we find the Lyapunov function, we can estimate the security region or the region of attraction. So essentially, the largest sublevel set within the valid region defines a security region. So we first test this algorithm in a grid-connected microgrid for proof of concept. So in this test system, we only have one microgrid connected to an infinity bus. We using the algorithm, this is a function Lyapunov function we find, and as you could see, the function indeed behaves like a Lyapunov function because it is a positive definite within a region, and its time derivative of the function is a negative definite. All the function value below 0. Here, all the function value is above 0. So next, let us compare the approach with the existing approach. Here is a conventional approach. So in this approach, the Lyapunov function, they assume the Lyapunov function has a quadratic form. So let's compare our approach with this conventional approach. The red figure essentially summarizes the comparison result. In this red figure, the red circle is we learned from the neural network. Basically, is the region of attraction, and the blue circle is from the conventional approach. And the red solid circle is larger than the blue solid circle. suggesting that the proposed approach is less conservative than the conventional approach. Let's do another simulation to validate this statement. Suppose due to some disturbance, the initial state start from this yellow point, and the yellow point is within the red circle, but outside the blue circle. So our approach can conclude the asymptotic behavior of the system, meaning the system trajectory start from this yellow circle will turn to the equilibrium point at the end of the day. But the region of attraction from the conventional approach can conclude nothing about it. If we do the simulation, we observe indeed the system trajectory turn to the equilibrium point. So we tested this algorithm. We do the similar practice in a slightly larger system. It's a IEEE 123 node test feeder. We divide this test feeder into 5 microgrid, and we assume microgrid 5 enters the island mode, and we want to assess the stability of the rest of 4 systems. Based on the algorithm, this is the security region we learned how to use this security region in real time. So after the microgrid 5 it enters island mode, we can collect the interface measurement x0, and we can plug the x0 to the optimal function. And this inequality tells us the initial state is within the region of attraction, suggesting the state will return to the equilibrium point. We have this statement without doing any simulation. If you do some simulation we can validate that the system trajectory indeed turn to the equilibrium point. So these 2 figures essentially visualize the optimal function learned and its time derivative. Is a positive definite function, and its time derivative is a negative definite. And this slide shows the visualization of the function in other space. So finally, we compare the function, compare our approach with the existing approach. In this figure summarizes the key result. The red solid circle is the region of attraction we learned, and the blue circle is what from the conventional approach. So again, the red circle is greater than the blue circle, suggesting the proposed approach is less conservative than the conventional approach. This is visualization of the region of attraction in outer space. So here is a summary for these 2 examples. In this presentation, we present the opportunities and the challenges in massively digitized power grid, and we propose a physical interpretable approach to false oscillation localization. This is a purely data-driven approach, and we introduce a learning-based framework for transient stability assessment of the network microgrid. So finally, I would like to point out the future direction by envisioning next generation energy management system, future EMS. Before talking about the future EMS, let me show you how today's EMS works. So today's EMS have 3 key functional blocks. The first block is about monitoring. This block aims to detect, classify, and locate anomalies using real-time measurements. Once an anomaly is detected, we have a mitigation block. This, as its name suggests, this block aims to take some corrective action to mitigate the negative impact of the anomaly observed. So for example, in the case of the false oscillation, the mitigation, the corrective action is to trip a generator causing the false oscillation. So sometimes the corrective action may change the dynamics of the system. As a result, it's possible that we solve one problem, but create another one. So how to address that in today's power system? In today's power system, we have an adaptation block. So this block aims to assess the feasibility of the corrective action. This is typically implemented offline. For example, in the transmission system, we do extensive N-1 contingency analysis before we operate the grid. This classic architecture can be traced back to an old paper written by Diliaco a half-century ago. And this architecture served the power grid for the past few decades. So next, let's talk about what the future EMS looks like. You may have your own version. Here is my version. I believe there are three driving factors for the EMS transformation. The first driving factor is the digital solutions. Digital solution actually enrich the functionalities in each block. For example, for monitoring, we have the advanced sensor such as the PMU or point on the wave data allow us to observe even faster dynamics. And the power electronics interface can enrich the actions in the adaptation stage and the mitigation stage. So second driving factor is about cyber threats. The increasing cyber threats actually redefine the anomaly. Anomaly is not only defined by the physical anomaly, but defined by the cyber anomaly. How to develop a EMS system that can monitor and take corrective action for both types of anomalies. The third driving factor is about deep renewables. Deep renewables add unprecedented uncertainties to the grid operation. So the grid operation, the behavior of the grid becomes less predictive than before. So we need to take some adaptation activities from offline to online. So this is my version of the future EMS system. To achieve this architecture, there are some open questions. The first question is how to add more values to streaming data. So today, while we have faster sensors, most of the time we only use this faster measurements for post-event analysis. We still need a tool that can translate the high-dimensional data into reliable decision that can directly apply to the grid. And how to address anomalies through reprogramming the grid. So instead of adding treating physical components such as generator or load to or adding new control loops to address the anomaly. So the question is how to address the anomalies through reprogram the dynamics of the system. It is possible because the future grid dynamics is not only defined by the physical components such as a generator, but also by the algorithms embedded in the power electronics interface. The third question is how to develop an online safety certification procedure. So instead of besides conducting time-consuming EMT or electromechanical simulation offline, so can we develop a even faster and rigorous way to certify the safety of the grid in real time? These three questions relate to my current research. And this is the last slide, and I'm happy to answer questions.
Thank you very much, Tong. This was quite a bit of information. So maybe we can start here with questions.
Yeah.
There is a question by Sivaranjani. Do you want to raise your question? I think you are unmuted, so you can unmute yourself and just raise the question quickly. Sitaraman. Okay, we can read it.
Hi. Sorry, yeah, I was muted. Yeah, so it's nothing. It was just this thing in the procedure. Tong, you had mentioned that if you have the first step is to check if the linearization is stable in the neural Lyapunov approach, but that's not, the stability of the linearization is not a necessary condition for the stability of the nonlinear system. So you could have a linearization that's unstable and still have a nonlinear system that's stable. So you would have to check both. So that's
true. That's indeed a sufficient. It's not a necessary condition. This is a sufficient condition. Yeah. It may cause some conservative. Yes, you are correct.
Yeah, it might be more conservative if you don't check that. Yeah.
Right. You are correct.
Okay. Yeah, and so if I may also tag on to this, I had one more question. So in the first part in your the matrix decomposition, you mentioned that the resonance, the eigen, that there's a second order sort of resonance term. So how did you actually arrive at the conclusion that that's second order?
Which you mean the interpretation for the
the interpretation for the PCA, yeah.
So essentially, what do you mean by the second order? I didn't follow that part.
No, so you had a slide where you showed the resonance, and so you had decomposed the waveform into the resonance and non-resonance. Could you go back?
Show that slide again,
right? The forced oscillation localization.
Yeah.
Yeah, that one. Resonance and resonance free. So there was the first part was it was rank 2, right? So how did that come about? I was just curious.
All right. Basically, if you you can write the closed form solution for this time domain measurement, right? Then basically it's related to the eigenvalue of the system. First, you can collect all the resonance components and formulate all the resonance components into a matrix. You can prove that the matrix has a rank 2, only have a rank 2 because it only involves cosine and the sine terms in each column.
Oh, I see. Okay. Thank you.
So then I think you have a related question on rank. Maybe you want to say your question. How was the rank determined?
Oh yeah, actually I saw the your formula that y equals z plus x, and you have some rank conditions. Can you so Tong, can you come back to that slide?
Oh, sorry.
Yeah. So you have like a rank z less than or equal to r, and the zero norm of x is less than or equal to p. So how do you determine the value r and p?
Here we don't have to determine the value of r and p. Here I just the reason I put this inequality here, I just want to say Z is a low rank matrix and X is a sparse matrix. So we don't have to determine these upper bounds R and P.
Okay, so does that mean that your optimization framework can guarantee that the solution would give us the low rank Z and the sparse matrix X?
Right. But the rank may not be greater than 2, and actually, if you have the rank 2 condition is only for you for the case when you only have one source and your periodic input is only contains one frequency component. If the source contains more than one frequency component, the rank may not be 2, it may higher, but compare with the dimension of the measurement, so it's still low rank.
All right, thank you.
No problem.
Maria, you're muted. Maria, you are muted.
Sorry, I talked, so I'll repeat.
Oh,
I was muted.
Sure.
Okay, so it concerns this vision that you gave for control centers for the future, it looks to me still that it's highly centralized. Do you see interactive gathering of data with different layers and decision tools at different layers affecting each other? So the control center itself becoming more distributed and interactive rather than centralized. And that is sort of very big difference with Diliako's vision, which says there is bulk power system and everything else we just assume based on historic data or pre-programming. Can you comment on that a little bit?
Yeah, that's a very good point. Instead of have a centralized control center for a large scale power system, perhaps we can inject some intelligence at the grid edge. The good thing for that is because if you have a centralized control center, you have to address high dimensional data. So it's sometimes it's a computationally computationally costly, and you need a very fast computation, both algorithm and hardware to address this high dimensional data. So that's one point. The second point is that sometimes we may not able to collect this high dimensional data because different entities have a different privacy preference. So the question is how to make the decision making near the source that's generating the data. So that's
so I know you're coming to us to do your second part of postdoctorate in January. So we are working at MIT quite a bit on what is the minimal information that must be exchanged for different applications. And so I think it would be very interesting to see who can get what information the best way. Like if you think about wind power plant, they know better what the wind is going to be at their location than the system operator. On the other hand, system operator has a better view of the overall grid status and so forth. So I think there is a whole set of issues there on how do we gather the information and how do we trust the information and where do uncertainties come from. So how do you see the data enabling help manage uncertainties? What is your general view on that? There's going to be a lot of uncertainties now. Who would be responsible for what functionality and even violating the standards and so forth?
Yeah, that's a very good question. For system operator, I think they should provide some high-level monitoring function to monitor and take some correction for both physical and cyber anomaly. And at the grid edge, I think, for example, the wind farm, they may have a more accurate when the generation historical data. They can provide some prediction for the global decision making.
Okay. I wonder if there are any other questions by the audience. Please feel free to just ask the question because nobody is muted here. You can unmute yourself. Are there any people who want to ask questions? So I'll ask one more. I think we have just a little more time. I think I forgot if it was page 26 or 30 when you posed the model of the microgrid. Can you look at that slide again?
Sure.
I forgot exactly if it was 26.
I think
that one, yeah. Yes. So I have some questions. My old advisor, I'm getting older myself, but my advisor, like 25 years ago, heavily criticized this idea of writing voltage dynamics with the voltage dV/dt. So can you explain where these two equations, the dynamics in the microgrid, comes from? And then there is another question, follow-up question here. These algebraic constraints, they're nonlinear. So how do you combine whatever you thought that was dynamics in the nodes with nonlinear constraints to get out of BAEs, but just have ODEs?
Yeah,
So I know it's a loaded question, sorry.
Right. Let me first answer the second part of your question. So essentially, this power flow equation, the input for this nonlinear equation is the delta and the voltage, right? And you can plug this real power and reactive power into the first order differential equation.
So we assume decoupling?
Yes. Okay, I know this is a broad assumption, and our ongoing work trying to, include more detailed dynamics into the framework.
Okay, that answers my question. I'm hoping to work on that more when you come in January.
Yes.
Okay, yes. And the other one is these dynamics of V dot. Mm-hmm. Where does that equation come from?
This equation basically is this voltage loop control. The voltage change according to the measurement of the reactive power. We change, sorry, the other way around. We need to change the reactive power injection according to the voltage magnitude measurement. This is the loop control or voltage loop.
So this is closed loop dynamics after the equilibrium of the very fast dynamics in the filters and so forth has settled, right?
Right. Let me show
you are
you
capturing the dynamics that's relevant on the distribution network, but not on inside microgrid.
Right. We didn't, because we assume there is a power electronics interface between the microgrid and the distribution system network.
Okay. All right, that answers my question. And I think we just have one more minute. I don't see many more questions. So thank you very much. There is a lot of food for thinking here. As Tong explained, things are changing big way. And the group at Texas A&M led by Professor Shilu and postdocs and grad students, they're actually on the cutting edge and doing a lot of outreach, I would say, with working groups in IEEE on these aspects of connecting the data and the physics in the future energy systems. So please reach out to them if you want to learn more about the working groups and if you have more questions. But for now, thank you very much, Tong, and we will we'll continue our discussions.